Okay, so on to chapter 13 in EE213, uh, and this is about magnetically coupled circuits, which are actually going to be inductors. So I will say I like the introduction here. Electromagnetics is a branch of electrical engineering or physics. It tends to be the most difficult of the electrical engineering disciplines because of the electromagnetic phenomena. So a lot of times there are physicists who are modeling the electromagnetics. But electrical engineers who specialize in electromagnetics are needed in the microwave industries, radio, broadcasting, antennas, research labs, and probably higher than a bachelor's degree is needed to actually have a full job in electromagnetism. A lot of math and a lot of simulations are done in electromagnetism because you can't see the um, electric or magnetic fields. You have to model them or see the result of their presence being there. So anyway, just to recall some demos I did in the class with the magnets on the magnet cart. I have some pictures of some other cool electromagnetism demos that you could do. In this case, we just have a coil of copper wire here. It's got an insulator on it. We call it magnet wire. Sometimes it has a ceramic insulator on it. So it's wrapped in a coil, and here's a double A or triple A battery, and it just applies current through there. It makes a magnetic field with a north and south pole, which will cause this little coil to spin above the magnet. There's a magnet down below here. So when the current is coming in here, it creates a north and south pole, so this little thing will spin. You can also wrap a coil around a nail and you'll make a north and south pole. You'll make an electromagnet, and you can pick up some pins or iron filings with this electromagnet that you've created. This coil here, it's actually kind of an important little thing when we talk about transformers. Down below I have a cross section of the coil, a bunch of wires here, a bunch of wires here, and you can see the magnetic field it creates, or at least we have a cross section of it, like I've sliced this coil in half and looked at the magnetic field that's produced by current in this coil of wire. In a transformer, you have AC current flowing in primary side, which we saw in the lab, and then it will produce a current in the secondary side of the transformer. So in this picture I have the magnetic field lines shown that is produced by the current on the primary side. And then these magnetic field lines you can see couple over onto the secondary side, and since there's a time varying magnetic field overlapping these copper wires on the secondary side, time varying magnetic field across a conductor will produce a current. So current will get produced on this secondary side. So that leads into the material out of the textbook. So we have a picture of a single coil in a circuit, which is an inductor. I mean, that's an inductor, but I don't have the secondary inductor, the secondary winding, or the secondary side of a transformer shown yet. Right now I'm just talking about what's happening in a single coil of wire or a single inductor. So if I pass AC current through this inductor coil of wire, it'll produce a magnetic field. And the size of the amount of magnetic field around this coil is called the magnetic flux. Magnetic flux has unit of Webers down here. Your book doesn't tell you the units, but the units of Webers are important. And Webers are actually a volt times second. So units of flux are Webers, and this time varying current through the inductor will produce the magnetic field. It's also a time varying magnetic field. Let me grab my pen here. So, okay, this is fine. So the magnetic field that's being induced in this coil will also produce a voltage across the inductor. And we know that to be true also. So when the current changes in a circuit, an inductor can be made to have a voltage induced in it. So the voltage across this inductor is proportional to the number of turns of the wire and the time rate of change of the magnetic field. So if you think about that, if I'm passing a coil of wire through a magnetic field, a voltage will be produced in this wire. That's what this equation is telling me. But we know that the magnetic field that's produced is actually proportional, actually depends on the current that's in the wire. So I have magnetic field as a that changes as a function of the changing current, which is d phi di, and times the rate of change of the current, di dt. So this fundamental equation right here is rewritten by actually sort of factoring out the differentials right here, which is perfectly valid because you can actually cross out the di dt's and you get d phi dt, which is back up here again what we had, d phi dt. So the voltage induced in the inductor is proportional to the number of turns in the coil, and then the rate of change of the magnetic flux due to the current times the rate of change of the current. And if you remember way back a few chapters last semester, that this term right here is actually the definition, corresponds to the definition of what an inductance L is. So the voltage in the inductor is L di dt, and we already knew that, but these equations up above have tied it to the magnetic field. So when this single inductor up here is producing a magnetic field, if I bring in a second inductor nearby, so here's my second inductor being brought in close proximity to the first inductor, and the magnetic field that this inductor is producing will overlap into this secondary coil over here. And since I have a time varying magnetic field going over this secondary coil of wire, a current will be produced on the secondary side of a transformer. And that's how it works. So the voltage induced in this secondary side, which is called the induced EMF, is proportional to the amount of magnetic flux that's passing over the coil, and as well as how many windings of the coil there are, how many turns of the wire. So that's what this equation right here tells us, that the voltage on the secondary side is proportional number of turns of the secondary side coil times the rate of change of the magnetic field. And once again, we can break down that rate of change of the magnetic field because it's proportional to a current, and in the end we get an equation that looks like this. At the voltage in 2, it has this term called M, which is called the mutual inductance, and then times the rate of change of current, the di dt, from the primary side. So it's a coupling coefficient, if you will. It says that the voltage on the secondary side, V2, equals some fraction, some proportional amount, which we are calling M, the mutual inductance, some proportional amount according to the changing current from the primary side. And it works vice versa too. If I have a current on the secondary side, it'll make a magnetic field which will induce a voltage back onto the primary side. And it's symmetric, so M12 mutual inductance of coil 1 to coil 2 is the same as mutually inductance of coil 2 to coil 1, hence the word inductance, mutual inductance. I will say that also the units of M, if I look at what the definition of M is right here, M is going to be an N and a d phi di, and if you notice, N d phi di is also the definition of inductance L. So the units of the mutual inductance is also L, or henries. So this is in henries, just like an inductor is, and inductance right here is in henries, also units of henries. So henries times di dt, and over here you see henries times di dt, which is amps per second. So If current enters, this is the dot convention that we're going to learn about. If current enters this way on this coil and I have it marked with the dots on the same side, then my coupling coefficient is positive. So V2 equals M di dt. If it's marked this way with opposite polarity, then my coupling coefficient will be negative. What that actually means on this transformer, the top one, part A, when the dots are on the same side, they're also said to be in phase. So the output will be in phase with the input, meaning when I1, if I1 is at a maximum, it will be something sinusoidal, right? I2 will be at a maximum at the same time. So they are in phase. This one is out of phase, so I1 max is at a maximum, but at the same time I2 will be at a minimum. It will be out of phase. So output is out of phase with the input when the dot convention is opposing like this. Why is this true? This is true because maybe the primary side, the coil is wrapped. I can't really draw. You can't tell from the drawing. Maybe the coil is wrapped clockwise here and clockwise here, or it could be the coil is wrapped clockwise on the left side, but opposite counterclockwise on the right side. So it's the direction that you've wrapped it. How can I say? So looking down from the top, if I look down from the top, maybe the first coil is wrapped this way, going down, down. Well, it's hard to draw a 3D picture, right? I can actually draw a 3D picture. I'll put a cylinder showing like where the wire is wrapped on it, and maybe this side the wire comes in, it wraps, it goes around, it goes around, and it goes back out. And it may be on the opposing side. This is where the dot convention comes in. My wire could come in. I could go behind or in front, right? So maybe I went this way. So that gives you the idea of where the dot convention comes in. This wire could be wound in this direction, like this, or this wire could be around the opposite way, like this. And that will give you the opposing or not. And the way to determine that was with the right-hand rule if you're using conventional current flow, or the left-hand rule if you're using actual electron flow. That's not the point of this chapter, but that's where the opposing, the in-phase or out-of-phase dots come from. So this chapter is really about how do I work with that from a circuit point of view. And if I have two inductors in series, and I can put the dots on the left side of both of these inductors and make that corresponds to a positive mutual inductance, and you would actually have a total inductance in this circuit. Although I imagine the mutual inductance is rather small because these two inductors are not close together the way it's drawn. But when you connect two inductors together like that, it's called a series aiding connection. So you would have the inductance total being L1, L2 plus the mutual inductance. And in the second picture, the dots are on the opposing side, so you can imagine that they are opposing each other, being out of phase, and the total inductance will be with a minus 2m factor in there. So that's a series opposing connection. So I'm going to go back for a moment and talk about what your textbook is calling the mutual voltage, and it's really the induced voltage. For example, the presence of this secondary coil induces a voltage on the primary coil and vice versa. So this term right here is an induced voltage. So a voltage is induced on the secondary side due to the current that's on the primary side, because it's I1 times this mutual coupling M. But I'm going to talk about it a bit more. The book describes the convention as being if current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive at the dotted terminal of the second coil. So that's actually hard to figure out what they're meaning. So I found a different description here that I liked a little bit better, that was a little easier to follow. And then I'm going to show you by example what it's really meaning, because the dot convention is the most confusing part, especially when we get to the circuits. So it says if current enters the dot, so here I1 is entering, I1 is entering the dot of this circuit, entering the dot of this primary side. If current enters the dot of a coil, then the reference polarity of the voltage induced on the other coil is positive at its dotted terminal. So what that actually means, let me grab my pen because color is going to become important here. So current is going in this terminal. That means the induced voltage over here is positive at where the dot is on the secondary terminal. So I put here a plus sign and a minus sign, and that's indicating the voltage that's induced on the secondary side. So we could say that if I were doing like a loop analysis around this circuit, that I have, there's a loop analysis around that circuit, I have additionally this induced voltage that's minus first, and then it's a minus side and then a plus side. So my induced voltage here is shown in gold, and that would be equivalent to saying that this is a controlled source on this side with polarity going around the circuit. I hit a minus first and then a plus, so I can put a minus there and a plus side, and the amount of voltage that's induced on the secondary side of this circuit is given by M di1 dt. M di1 dt. So this figure 3a in your textbook is trying to illustrate this concept. So current, if current is coming in this side, if current is entering the dot of that terminal, that means the induced polarity on this side will be positive here where the dot is. And so I can come over, and I know there's going to be an induced voltage on the secondary side. It's this guy right here related to the coupling. Take that off. But I don't know what polarity to put on it. So the way you determine the polarity is, plus is on this side, minus is on this side, is by the rule I just described here on the right. So you can see now plus is put in on that side and minus is put in on that side. So I'm going to show by more examples here in a minute, but the other aspect is that if you show current leaving the dotted terminal of a coil, then I'll show by example. If current is leaving, so the dotted terminal of a coil, then the polarity on the induced other coil is negative at the dotted terminal. So I think this is probably best shown by example. So let me go to my example because the textbook didn't make it very clear. Okay, so the first thing that I want to say about this problem, this is one of the examples in your book, is I can choose to solve a circuit problem in the time domain or in the frequency domain. And your textbook is a little bit confusing as they draw these like they're a DC source, but remember that that these are really AC circuits. DC would not make sense in a transformer. DC cannot get through a transformer because there's no DI dt in a DC. So even though your textbook drew those like DC sources, they are in reality AC sources, and I wish the textbook had drawn it that way. Likewise with this one, that is not a DC source, it is an AC source in the circuit. So now I can analyze this circuit behavior in time, or I can analyze it in frequency. It's actually either one will give you the correct answer, but I will tell you right now that analyzing a circuit in the frequency domain is more often easier than analyzing it in the time domain. Nevertheless, if we wanted to analyze it in the time domain, we would write a loop equation for the left loop and a loop equation for the right loop. So it's going around the loop IR1 plus voltage in the inductor, which is LdI1 dt, plus the additional amount of voltage that's induced by the current in I2. So looking at my dot convention, I have current going into this inductor. So that means the induced voltage on the secondary side has this polarity, which is equivalent, if I'm writing a loop equation on part 2, on loop 2, that's equivalent to, so plus hits first, plus hits first, plus hits minus. So that's equivalent to saying a little induced voltage is over here in this loop when I write the loop equation. So that it's mdi dt is the size of it. Similarly, and I'll change color to help keep track of the accounting here. Similarly, I have current going into the dot on this side, so that means that on the primary side, that the polarity of the induced voltage from the secondary side goes this way. The positive is at the dot. That's equivalent to putting a little induced voltage in my mesh equation right here. That's positive, negative, and so I'm writing a loop around here, and I get the, here it is, the plus mdi2 dt. So there's an mdi2 dt. And now I have two coupled differential equations, two equations and two unknowns. We could solve that with differential equation techniques. It's not very nice, but we could do it. However, we could also solve the problem in the frequency domain, which is easier. If our voltage sources have been turned on for a long time, we are in the sinusoidal steady state, and we can use phasor notations. So my voltages and currents, which have phase relationships and are complex numbers, or their magnitudes and phases, are all shown as bold things right here. But if I write my loop equations here, I get the same result as on the left-hand side. Yes, you do. So I think that the best thing to do now for us is to show an example. So we will now show an example. Okay, first example has the dot convention such that the secondary side is in phase with the primary side. So I'll just set this problem up. We don't need to crunch through all the numbers, but I want to go through the dot convention, and then our next example we're going to have the dots be opposing each other. So I'll show you how that works, which we'll use our second dot convention statement. So let me pick, we'll start with writing the loop equation for the left-hand side. I see that current is, actually we'll start by writing the loop equation for the left-hand side. So the left-hand side, the primary side, has some voltage induced in it from the secondary side. But I'm going to write the loop equation for the first side first. So I see that I have the coupling, the mutual coupling right here already given to us. So remember that m di dt has units of henries. Actually, it doesn't, does it? It's units of ohms altogether. Yes. Okay. So anyway, so I have current, and look at what my current is doing. It's coming in by the way we define this loop current. It's coming here, but it's exiting. It's exiting where the dot is, correct? So current is exiting where the dot is, and my dot convention says if current is leaving the dotted terminal of a coil, the reference polarity of the voltage induced in the other coil is negative at its dotted terminal. So that means that this current is leaving. That means the induced voltage on this other coil is going to be negative at the dot. So my induced voltage is going to be in this direction on the primary side. And I'm going to change color to keep things, well, I guess I can look at it. So look at my polarity here. It's negative and then positive that direction in the loop. So I can write an equivalent circuit with that induced voltage in it, which is what's shown in figure B over here. And notice that the induced voltage in loop 1 from loop 2 has the polarity given by my blue polarity signs. And the size of it there is this mutual inductance right here, J3. But it's J3I2, and we're in the frequency domain. So switching colors, I'm going to switch color to make sure it's clear here. Now we want to look at the loop 2 here, and it's going to have a voltage induced in it from the current in loop 1. And so I see current going into the dot here, so that means that on the secondary side, current into the dot will have polarity this way on the secondary side. So if I look over here, that means going around this loop, I have a little voltage induced in this loop from the current in loop 1, and it's the polarity given here. So that's this little extra voltage in the loop right here. So now I almost want to say I've decoupled these two loops and made them more analyzable. And so if I go now and analyze it, I can write the loop equation 1 pretty straightforwardly. That's 12 plus 0j. And I write my equation around the loop. 12 equals I1 minus J4 plus J5. And that is, remember, going around the loop, put our polarities on, everything goes, current in is positive, current out is negative for these components. But this one, the sign is different, so it's plus J5, but minus J3. Oops. Different. It's not. So it's a minus J3I2. So that's the loop equation for the left loop. We can write the loop equation for the right loop. I'm going to go ahead and put my little polarity housekeeping things, marks on my loop. And I have I2 times J6 plus 12, the resistor, and then there is a minus J3I1, and that equals 0. So now I have here two equations and two unknowns, and I can solve for the currents I1, I2, just keeping in mind that these are all, of course, complex numbers and it's phasor notation, and I may have to convert back to a trigonometric form in the end with magnitude and phase. But that's how you would go about solving that problem. Okay, let's try a more complicated problem now, which is really going to hit home this mutual inductance, this mutually induced voltage that occurs from the two inductors being in this circuit. So let me switch colors. We're going to need a lot of colors on this circuit. So I'm going to start with purple. So let's look at loop 1 first. So loop 1 has I1 going into this coil. So this induces a voltage in the other coil, which is this J8 coil on loop 2. So what does it induce? So I1 is going into this coil, into the dot. That means the induced polarity is positive at the dot of the other coil. So that's what and the size of it is J2I1. So this little voltage has been induced in the second coil due to the current in I1. And just so that I can help keep track of this, I'm going to put my little dependent source over here with the polarity minus plus in purple. Okay. So that's what current 1 in this inductor does to the other inductor, the J8 inductor in coil 2. So that's one down. So now we have to look at the other direction. What is current in the second inductor doing to induce voltages in the first? Well, let's not finish. Let's finish the first one first. Sorry, there's more to be added here. I should have started with the easier one first. So I'm going to change color now. We also have I2 going in to this coil. It's actually coming out of this dot. So I2 is there. So I2 in the first coil induces a voltage in the secondary coil. So I2 is leaving the dot. That means in the secondary coil we have a minus plus that polarity. It's minus at the other dot, and it's J2I2. So the presence of I2 in this first coil induces a voltage in the secondary coil. And that one, this little dependent voltage, I'm drawing it here in blue, has polarity this way, and it is J2I2. So I have I1 in this coil inducing something in the secondary coil, and I2 in the center coil inducing something in a voltage in the coil in the second loop. So I'm going to switch colors again. I'm going to switch to this color now, and I'm going to see what the current in the second inductor is doing to the first inductor. So I have I2 is leaving that dot, so it induces a voltage in the other coil over here where negative is at the dot. So I am going to induce a voltage on this coil, negative, positive, and it's J2, and I'm going to draw that little dependent source in here, dependent voltage, and it has this polarity. Okay, and I think we're missing one more, or do we have them all? Okay, so I2, and then the other funny thing is that the presence of, okay, I got that. I think no, I do have them all. So now we're ready to write our loop equations, and I am going to change color one more time. The way I'm going to write our loop equations is first, just like we did when we wrote loop equations before, I'm just going to go around the loop. I'm going to put some polarity markings on the components based on the direction that I've drawn my current loop. So, and I've changed colors here. And this one's going around this direction, so it goes this way, this way. So I got a lot of polarity markings here. And I'm going to write a loop equation around the loop without regards to the induced voltages, and then I'll add the induced voltages in. Nah, I guess I can go around the loop straight. So this is really 100 plus J0. So let's do around loop 1. Let's do Kirchhoff's voltage law around loop 1. So I have 100 equals I1, and we'll do it very explicitly just to make sure it's clear. I1 times the resistor, so it's I1 times 4 ohms, and then it's plus I1 times minus J3, right? And then right here it's plus I1 J6, but it's also minus I2 J6. And oops, I forgot there's a little voltage right here. What is that little voltage? It's that induced voltage there is minus J2 I2. I left off the I2 over there. Minus J2 I2. Put that on there. Minus J2 I2 because it's due to the current too. Okay, so I wrote the loop equations around node 1. I simplify that and I get, and voila, I get this simplified math, an equation for I1 and I2 for loop 1. Now let's do loop 2. So for loop 2, I'm going to do the same thing. I'm just going to go around the loop, and I'm going to make sure I include these dependent sources. And when I hit this inductor in the middle, it's I2 times J6 minus the other direction, I1 times J6. So I think I'll start right here, going around the loop. So that's I2 times 5 ohms. Now I'm here, now to this next component, which is plus I2 J6 minus I1 J6. Now I have this little induced voltage right here, which is a plus, by the polarity markings, plus J2 I2. Coming around the loop, I have now a plus J8 I2. And now I have an induced voltage, which is a minus J2 I1. And I have another induced voltage, which is a plus J2 I2. And now I've completed around the loop, and it's 0 equals 0. I will simplify. There it is rewritten. One thing I want to point out here is that due to current I2 goes through 2 inductors. So I'm looking to show you that, let me skip back a slide. Back here on this, if I have two inductors in series with each other, and in terms of I2 they're in series, then I should have a plus 2M. So I should have a series aiding connection here. So let's see if I really do. So on this circuit, the current, or all of the voltages for made by current I2 does have a J2 that appears 2 times. So I have a 2 times the mutual inductance occurring. So these are series aiding inductors. So now it's just a simple matter of simplifying this the rest of the way, and then you get I2 5, let's see, 14, 15, 16, plus J18 plus I1 minus 8J equals 0. I now have 2 equations and 2 unknowns, I1, I2, which you can solve for.